it takes a little trick to do, but it's a very neat one. F of x is e to the minus x squared over 2. You recognize that as an important function, e to the minus x squared, or it usually has that e to the minus x squared over 2, or sometimes an e to the minus x squared over 2 sigma squared, a rescaling. But this would be the bell-shaped curve. The bell-shaped curve. It decays very quickly. The variance, because that's a 2 and not a 2 sigma squared, the standard deviation is 1 here. The variance is 1, so it's a bell-shaped curve that has about 2/3 of its area between -1 and 1. This is the all-important function for probability. The normal distribution, the Gaussian, both of those words are used, is the most important probability distribution. I need a 1 over square root of 2 pi to make the total probability be 1, but let me just leave it there. That's a very, very important function. It's also going to be important in the heat equation. It just, in math finance, shows up all over the place. And its integral would not be easy to do from 0 to 1. From the integral of that function from 0 to 1, we have tables of it, to the nth place. But there's no simple elementary function whose derivative is this. That x squared is what's making the integral tricky. So from 0 to 1, we just have to give it a name. So error function. This would be ERF, error function, the integral of that thing correctly normalized. I'm just saying important function. But and it turns out that integrals from minus infinity to infinity can be done. So beautifully, by some trickery, we can find the transform of this thing. We can find the transform of this. We can do this integral from minus infinity to infinity where we could not do it from 0 to 1, for example. So I'll just write down the answer for this guy, only because it's such a key example. It's some constant that involves 2 pi times e to the minus k squared over 2. Boy, that's pretty amazing, right? The Fourier integral has the same the Fourier integral transform, f hat of k, has the same form as the function. That's, and of course, this function is infinitely smooth, so its transform decay is infinitely fast. There's no problems like 1 over k squared here. There are no bumps in the bell-shaped curve. So I won't push that example, except I'll use it. What else should I say just to emphasize that this is such an important distribution in probability? Why is it important in probability? That's the question. Why does everybody assume if you can get away with it and don't have any natural alternative, everybody assumes that noise, whatever, is coming with a normal distribution. So, in other words, with a sigma squared in there. So normal distribution that has mean 0 because it's absolutely centered at the origin, and it has variance 1. But I could change the variance, and that would just spread out or tighten the bell-shaped curve. Why is the bell-shaped curve so important? That's certainly, we're not going to launch into theory of probability, but it's the central limit theorem. So let me just use those words. The central limit theorem that says that if I start with other probability distributions, like I'm flipping a coin, I flip a coin 1,000,000 times. Then the mean, and let's say 0 for tails, 1 for heads. Okay, so I flip. Well, the mean of that, the expected mean is what? 500,000, right? Half tails, half heads. So if I give 0 for tails, 1 for heads, and flip 1,000,000 times, the mean would be about 500,000. And then, so let me center the mean. Oh, yeah, I could have centered it by taking -1 and 1. That would have been smarter. -1 and 1. -1 for tails, 1 for heads would have had a mean of 0. And then it would be natural if I have 1,000,000 of these to divide by 1,000, I think. I'll count. Of course, the answer won't be 0, right? If I do 1,000,000 flips, it's not going to come out exactly 500,000 and 500,000. I'm remembering, I used to have a long discussion with a nice guy in college. He ran for mayor of Boston, actually. But he had the idea that after 1,000,000 flips, suppose there had been more heads than tails. Then the next flip, he figured, was more likely to be tails. I couldn't convince him that this was not mathematically the right thing to think about. And all I did was say, don't go to Las Vegas. I mean, if you're thinking that way, save your money. So, right. So anyway, but this is much studied. The variation, what that curve looked like, it's quite interesting. But my point is that as the number gets bigger and bigger, and we scale it properly, the distribution will approach the normal. All sorts of distributions. If I just repeat and repeat experiments and scale it, the central limit theorem says you're always going to the normal distribution. So that's highly important. Okay, and it comes up different places, and it's quite a neat function. Okay, so that's some examples.